Hey guys, welcome back to All Things Embedded, and today I'll be talking about the 2-bit binary adder. Kind of go over the logic here. Alright, so here we're going to condense this down to just one aspect of the adder, which is the XOR gate. So you can see here that there are three different versions of this. It can be condensed down to simply the inverted input flip-flopped with the opposite. But nevertheless, all the truth tables are basically the same. And I'll kind of want to talk about the third side here and why there are two different inverted inputs here. Well, when you try to connect the input of one AND gate to another set of resistors, it creates a negated logic. It essentially creates a NAND gate, which we don't want that to happen. So what do? We simply invert the inputs, which I'll show down here why it plays out well in the long run. So in discrete logic, essentially if you negate something twice on top of the current condition it's already in, you can actually take away both of these not symbols, and you can do the same with these. So 2 and 2 cancel out, which essentially leaves you with the same logic that we had right here. All right, let's take a look at the full schematic here. So when you kind of break down all the discrete elements and how they kind of fit into the overall picture here, I have each one of these kind of squared around, just to color code the inputs. We have the AND gates matched here. We have the two inverters, which are matched into these right here. And we have the last OR gate, which is matched into the last symbol right here. And I want to make a note that each plus 5 volt rail has a 1K resistor attached to it. All right, let's look at the example here. So here's an example of the 2-bit adder doing an addition operation here. So here are the four, numbers that are represented by 2 bits inside of digital logic, which is 0, 1, 2, and 3. And this last one here will actually create an overflow, which I'll show in a minute. It basically essentially creates a carry digit that can't be represented within a 2-bit system. So let's do an example. So say we wanted to add 1 and 2. So it would process each of these vertically, pass them into the adder, and then it would output it to the bus. So we're going to organize it by least significant bit and most significant bit. So this will be B0, A0, B1, A1. So let's say we have 1 go out into the bus, or into the adder. So 1, 0. So that means the XOR gate will go high, and the carry will be low. So that means a 1 is output to the bus. So now we have this set of digits done. So let's say we want to do B1 plus A1. So it's the same thing. 0, 1, the XOR gate's high, so the sum is 1. And kind of the key here is, if you want to memorize the XOR gate pretty efficiently, is that one input has to be different than the other input inside the gate. So if A is different than B, then it's automatically high. You can't have double ones or double zeros. So let's talk about the overflow condition that I was talking about earlier. So say we wanted to add 3 and 1. Well, what is 1 plus 1? It's 1 with the carry. So now you have a carry digit that can't be processed within a 2-bit system, in which you would have to create a Cout vector here and a corresponding Cin input here. But even if you do this, 0 will be output to the bus over this side, and on this side, we would have another 0 output to the bus, So now both these are 0. And then you would have an extra carry digit that can't be processed here. Because inside of a 2-bit system, you would have to account for the extra C out and C in within inside the XOR gate. So now, instead of just having to worry about A and B being XOR together, you now have a separate CN input. So it goes from just A XOR with B down to CN XOR with A, or B XOR with CN, or A XOR with B. Sorry for my handwriting there, but essentially CN creates a whole separate system in which it graduates from 2-bit to 3-bit, which I'll show in my next video. So how do we build this thing? Well, see here. So now I have the same breadboard from before, but disassembled. So now we're first going to start off with the AND gate and the OR gates. I have the schematic in the top right hand corner right here. So yeah. All right, now let's plug in our inverter inputs. All right, now let's construct our inverters to be put into the OR gates. All right, we have all our inputs connected, so let's connect the voltage. Gotta film this starting at like 12 a.m.
Guys, so it's now the next day. It's now.
All right, we have the truth tables here. So if we press 1, the white LED should, or the yellow LED should light up. That's our XOR LED there. And if both buttons are pressed, then our AND gate should light up, which is the blue LED right here. I'll remove this one. This one doesn't matter. All right, let's call this one A, this one B. So if A is high, yellow will be high. If B is high and A is low, it should also light up. And if both are high, then our blue should light up. And the current should be drawn from this side to this side, this AND gate right here. So yeah, it's basically how to build a 2-bit binary adder. And thank you guys for watching. It wasn't flawless.